Newton's law of cooling. So in this video, I just want to chat about Newton's law of cooling and talk about why the differential equation representing the Newton's law of cooling makes sense. It really should make sense. I don't want you to treat this topic as a formula that's given to you and you just integrate it and memorize it. Because again, the formula should make sense. By the end of this video, I will have the differential equation set up and explained. I will post a second video that walks you through solving this differential equation. And I will also include one example in that video. I think it's definitely a good idea to watch this video first. So let's get started then. So Newton's law of cooling states that the rate of change of the temperature of the object is proportional to the difference between the temperature of the object itself and the temperature of its surroundings. Before we start analyzing anything and before I start writing down any equations, I actually want to answer some questions that people ask all the time. So questions like, why do we learn this? Why is this important? Or what are some applications? Keep in mind that this law has its limitations. So here we are assuming that this law works, and ideally, yes, this law works. But actually, if the temperature difference between the object and its surroundings is too big, then this law actually doesn't hold anymore. We also have to assume that the temperature of the surroundings or the ambient temperature is constant. Your science teacher can probably tell you more, but I just want to talk about those limitations at the math level. So we're moving on. One obvious application is that Newton's law of cooling allows us to predict how long it takes for a hot object or a warm object to cool to a certain temperature. So in this case, the ambient temperature must be cooler than the temperature of the object to start with. And the one really common type of question in calculus and or in science that you will encounter is the type of problem that asks you how long does it take for a cup of hot coffee or hot tea or hot whatever to cool to a certain temperature. And by the way, Newton's law of cooling actually also works for heating. So your teacher can also ask you how long does it take for a cup of cold water to reach a certain warmer temperature. But in reality, like really, who cares? So if you're trying to drink a cup of hot coffee, if the coffee is too hot, you can just wait 10 minutes and check back. And after that, maybe another 5 to 10 minutes if necessary. So no one is actually going to do math to figure out how long it takes your cup of coffee to cool to a certain temperature. Which makes me really want to mention my favorite application here, which is the application of Newton's law of cooling in crime. Well, not in crime, but in crime investigation. So once the investigators arrive at a crime scene, based on the ambient temperature and the current temperature of the dead body, they can actually calculate how long the person has been dead. Well, I'm not an expert, but I'm pretty sure if the body has been dead for too long, if the body temperature has already dropped to the ambient temperature, then in that case, actually, they have to measure the stiffness of the body instead. Probably sounds familiar to you if you have watched any sort of crime detective TV series, such as CSI and such as the Japanese animation Case Closed. Detective Conan in there has definitely talked about the temperature and the stiffness of dead bodies. 4 minutes of intro is enough. Let's do some math now. Let's define our variables first. The rate of change of the temperature of the object, so let's call it dt over dt. The capital T stands for the temperature of the object and little t is the time. Proportional to the difference between the temperature of the object and the temperature of the surroundings. So temperature of the object is once again T, and let's call the temperature of the surroundings T sub s. So we have T minus T sub s. So remember here, T sub s is a constant. Proportional means dt over dt is equal to t minus ts times a constant. Let's define that constant as lowercase k. Before we solve the differential equation, let's take a good look at it. Should make sense. This differential equation is telling us that when T, the temperature of the object, is close to Ts, the temperature of the surroundings, which means this difference, T minus Ts, is close to 0. And in this case, dt over dt, the rate of change of the temperature of the object, is equal to k, the constant, times a number that's really close to 0. So the rate of change of the temperature of the object is very slow. On the contrary, if the difference between the two temperatures is larger, then dt over dt would be equal to the constant k times a bigger number, or a more negative number if this is about heating. Either way, the temperature of the object is going to change at a faster rate. So if the temperature of the object is greater than the temperature of the surroundings, so T minus T sub s must be a positive number, then that means we're talking about cooling here. So that means dt over dt must be negative. In order for that to happen, that requires our little k to be a negative number. The second case, if T is less than T sub s, so the temperature of the object is less than the temperature of the surroundings, T minus Ts would be negative in this case. Also means we're dealing with heating here. That means the temperature of the object will be increasing, which means dt over dt would be positive. And in order for this to happen, our little k here must still be negative. Therefore, many people actually like using negative k instead of k. And in that case, the k that they're using would be a positive constant. There's probably a point to it in science using negative k instead of k.
But as a math person, a positive constant is a constant, and a negative constant is also a constant. So I really don't see the point of adding a negative sign in front. So I am just keeping the k as k, keeping in mind that my k here is a negative number.
Alright, I'm gonna end this video. The part 2 video will continue from here. I will solve this differential equation and I will give an example in that video. See you soon!